Okay, so Green's theorem works for closed curves. Let's see in this example how we can apply Green's theorem if the curve is not closed. So the idea is about the curve, so the function is irrelevant. So let's take any function of a vector valued function, of course in R2 of two variables. So if we take x squared y minus x as my function, and let's take the curve, let's see, be the upper half of the unit circle. Of course we need an orientation. Let's take it oriented counterclockwise. Then find the integral over c of dot dr. So in this example, this is our curve. This is the upper half of the unit circle. And when we say the upper half of the unit circle, remember the unit circle consists of two halves. So this is the upper half, this is the lower half, which means, if you agree, so the x-axis, this is not part of the circle. So when we say upper half of the unit circle, we only mean the green curve. This is it, which means clearly C is not a closed curve. If it's not closed, can we use Green's theorem? In fact, yes. So how do we use, this is the idea of this example, how do we use Green's theorem if my curve is not closed? The idea is, so this is my curve, the green curve, this is it. Let's close it. So if you want to close this curve, you add this piece. This is not part of the curve. So what we do is, we add it, then we subtract it. So basically, we say, okay, the integral over c, the green curve, I'm going to say, if you allow me, I'm going to say it's equal to the integral over the green curve. This is the c. But then, this is equal to the integral over the green curve plus the red addition, then of course f dot dr, then minus the integral f dot dr of what we added. So now we subtract the same curve and we subtract it in the same direction. So when we added it from left to right, then we subtract it from left to right. In this case, the first integral is done over a closed curve. That means you can apply Green's theorem. So this is the double integral of, what's the integrand? We go back to f. This is f. You differentiate the second coordinate. This is the second coordinate. With respect to x, that's minus y, 1. Minus you differentiate the first coordinate with respect to y, that is x squared. Of course, the a over the interior of your curve, which is this disk, half disk, minus the integral. Now for this other integral, this is a line segment, you just need to find the parameterization. And usually this idea is useful if what you added has a simpler parameterization than the original curve. So my original curve is a circle or a semicircle. It's a little bit, let's not say complicated, but it needs some computations with sine and cosine. But with this line segment, what we added here, this is really easy. So we find a parameterization. So what is a parameterization for this curve? After all, it's just a line. So if you agree, this is r of t equals, the y coordinate is 0, the x coordinate is t, and t is from -1 to 1. So this is from -1 to 1. You go back to f, you replace every t, every x by t, every y by 0. That gives you 0 and 0 minus t dot r prime, which is 1, 0. So we are very lucky that this integral is really simple. This is just 0. So what we are left with is the integral minus 1. Let's take the minus out. So it's 1 plus x squared dA over this half disk. Now to do this integral, the best way to do integrals over circular regions is to go with polar coordinates. So we replace the x by r cosine theta, we have a square. Then the dA is r dr d theta. Because you're dealing with a semicircle, the theta goes from 0 to pi, and the radius is 1, you go with r from 0 to 1. This is minus the integral. So now standard computations, r plus r cubed cosine square theta d r d theta. So let's change this. So this is 1, and this is from 0 to pi, minus integral 0 to pi. The r integral from 0 to 1 is half. The r cube is fourth cosine squared theta d theta. Then you need to do this integral. The half gives you pi over 2, and this gives you 1 over 4 times half plus half cosine 2 theta integral from 0 to pi d theta. This is just the identity. So this is minus pi over 2 plus 1 over 4 pi over 2, and that integral would be 0. So we're dealing with minus pi over 2 plus pi over 8, which is minus 5 pi over 8. This is the integral. So we use the idea of this example. We use the Green's theorem. Although the curve is not equal closed, by adding and subtracting a piece that closes